Okay, everyone, we're down to our last final day of new lessons for the week. So congratulations, you're there. Tomorrow's going to be review, and then the next day is going to be your mini quiz. We've talked a lot about the first fundamental theorem of calculus for the last few days. Today we're going to introduce the second fundamental theorem of calculus, and let's just jump right to it. We're going to have two videos today. The first one, I'm going to introduce to you what it is and how to use it. And then the second video is going to be some examples. So just to show you what it is, let's say we are taking the integral. Let's just do one at a time here. I'm only looking at this part right here, not this bottom part. Let's say we're trying to take the integral of a function t squared minus 3t with respect to t dt, so dt. But instead of two constants as our boundaries, we're going to have a constant as our lower boundary, but we're going to have a variable as our upper boundary. Okay, so to address that, let's take the integral and let's just go like we normally would and see where it takes us. Okay, so I'm going to start up here so I have room. So the integral of t squared would be t to the third over 3 minus the integral of 3t would be 3t to the second over 2. And it looks like our boundaries are from 2 to x. Okay? So nothing any different. We're just going along like we normally would. We're just going to plug in x instead of a number. So if I were to do that, I would get, instead of t to the third, I would get x to the third over 3 minus, instead of 3t to the second, I'd say 3x to the second over 2. Okay, so again, instead of plugging in a number, I just took my x and plugged it in wherever I see t. Okay, now I'm going to subtract out, and now I'm going to plug in the number 2. So 8 to the third, I'm sorry, not 8 to the third, 2 to the third is 8, so that'd be 8 over 3 minus t to the second, so 2 to the second is 4 times 3 is 12, divided by 2 is 6, so I'm going to make that 6 over 1, just because I know I have some fractions here that I'm going to have to combine. So if I did take my common denominators here, I'd multiply top and bottom by 3. This would actually turn to 18 over 3. So just to write this out, I would get x to the third over 3 minus 3x squared over 2. And then if I have 8 thirds minus 18 thirds, it would give me minus 10 over 3. So I can still take the integral. It's just going to be, my final answer is going to be in terms of x. Okay? So let's go in reverse, because there's going to be something interesting that happens here. Let's take the derivative of our answer. Okay, now we've always said in the past, if we take the derivative of our answer, we should end up back at our original integral. Okay, so let's see if that happens. Now we're going to have to remember derivatives. I'm kind of shifting gears here. Okay, derivatives, using the power rule, we subtract 1 from the exponent, remember? And then I bring the exponent out front. So 3 over 3, okay, 3 times 1/3 would just be 1, okay? So it'd be x to the, and then I subtract 1 would be 2. Okay, minus, bring the 2 out front, 3 times 2 is 6, divided by 2 is 3. X to the first, which I don't need to write first, plus, remember for derivatives, our constants always go away. So this would have been our answer for our derivative. So what are our observations? If we take the derivative of this, if we take the derivative of this answer, we get x squared minus 3x. Well, let's look at what we started with, t squared minus 3t. Hopefully you're noticing that it is the same thing. It's just we swapped out the variables, okay? So we took this x, and we plugged it here and plugged it here, and got the same thing as our derivative, okay? So in other words, let me just kind of sum this up. You'll see stuff like this on your assignment tonight, where you are taking the derivative of an integral, okay? And when that happens, if your lower boundary is a constant, meaning a single number, And if your upper boundary is just a single variable like x, a quick shortcut would be to say the final answer is taking x, plugging it in wherever you see your opposing variable, in this case a t. So this would be x to the third plus 6x squared. That would be my answer. So let me back up. The derivative of the integral of t to the third plus 6t squared dt, if my lower boundary is a constant and my upper boundary is just a variable, all I need to do is take that variable and plug it in to get my answer. Okay? The reason we can take that shortcut, like we already demonstrated here, if I take the derivative of the integral, I end up back where I started. The only difference is, instead of t's, I plugged in my x. Okay? We took the derivative of the integral, ended up back where we started, just changed the variable. Okay? So when you see problems like that on tonight's homework or today's homework, this should take you 10 seconds, right? You're just rewriting the problem with the variable, okay? The next video after this is going to demonstrate what happens if you see homework assignments where the bounds are more complicated. So in this case, t to the third plus 6t squared, your lower boundary is not a constant, it's x squared. Your upper boundary is 2x. So this is much more complicated than what you saw on my last slide. When this happens, we have to use the second fundamental theorem of calculus. So I'm going to do these two examples with you on the next video, but before we do that, please write down the second fundamental theorem of calculus. Okay? What this is the derivative of an integral from v to w, so lower boundary to upper boundary, is equal to f of your upper boundary times w prime minus f of your lower boundary times lower boundary prime, or v prime. Okay, so pause the video, jot that down, and we will use this on our next couple examples on our next video.